Undeniably, one of the last great challenges facing humanity has been the fact that lithium batteries are now a little bit rubbish, and so of course I'm always going to be on the lookout for the next big thing. And it turns out the next big thing might be sodium batteries, so we're going to do a bit of testing, including in the cold.
Sodium is frequently touted as the evolutionary successor in battery tech, even if not quite bringing revolution. We know its promises have caveats. It's fundamentally lower in energy density than most lithium varieties, and that can't be magically solved. It should be in time cheaper though, once there's economy of scale. At present they are sold similarly priced to lithium, or even at a premium. I'm interested in seeing how they perform at various discharge loads, how they charge, how they do in the cold, and what's up with their voltage range. This is the testing trio I settled upon. Old school lead acid, this one a small sealed unit designed to start small engines, so with a respectable CCA rating. It's the base, a reference for us. Old technology, but one that many are familiar with. In news that will shock you, lead is by far the heaviest and does not contain a battery management circuit or control system of any kind. I've picked one lithium chemistry from the many available, the most popular quote-unquote safe lithium, which is lithium iron phosphate, and has a lower native voltage than the lithium ion or polymer in your phone or camera battery. It's a little less energy dense, but usefully less susceptible to thermal runaway and general fire-related activities. And here's the sodium-ion battery. These are not readily available, and I had to do some hunting online, but you can now buy cells and both small and chunkier batteries from a handful of sources, all Chinese sourced as far as I can tell. Both these lighter weight batteries have a basic BMS, things like low voltage cutoff. More on those later. I want to test batteries repeatedly from full to empty and so on, so I've tried to source 3 small batteries that won't take days or weeks to discharge at low currents. It turned out to be harder than it sounds, but these should all have a nominal 4 amp hour capacity, and to not be too controversial all at once, they are a nominal 12 volts. But the bright sparks amongst you will know that nominal is a rather wide umbrella, and indeed not even one that everyone can agree upon. Forgetting the voltage range itself for a moment, the maximum fully charged 100% voltage for each chemistry is not even a settled matter. The reason being that most batteries throw extreme shapes at either end of their curves, and so 1 or 2% of capacity can span a large voltage range, especially so with some types. It means that you can, should you be that way inclined, argue about whether a fully charged lithium iron phosphate battery, rested, is 14.4 volts, or 14, or 13.8, or 13.7. But let's not dedicate our entire lives to this particular battle. Certainly no 2 charts online can agree. I'm calling a battery full when my charging system places it into float mode, having used the most commonly accepted charging profiles I can find for each type. This brings me to my charger for the test. As followers of Alan's outfitting will know, I have a series of very powerful Victron AC to DC 50 amp battery chargers, and they're the smart sort where the app gives you all sorts of information. Perfect, you might think, but holster your optimism, people of the channel. Their minimum charge speed is too high for 4 amp hour batteries, or at least most. No drama, I have a solution. The smallest, but still rather clever, charger of the Victron range. It runs at only 1.1 amps when fully wound up. Same control in the app, and importantly we can select whichever voltage we like, even up to 16 or 17 volts. You might not be that animated by this, but for sodium batteries we need high charge voltages, and they are not easy to find. This battery was delivered with a 14.6 fixed voltage wall charger, which cannot properly charge the battery it was sold with. I'm sure proper sodium ion rated chargers will proliferate, but not yet. Before we're carried away filling up and emptying little black boxes with electricity, I'll come to the other aspect of voltage range, the lower end, and so the difference between full and empty. Lead acid batteries range a little over 1 volt from full to empty. More on what we mean by empty in a second. Lithium iron phosphate are famously annoying as the majority of their capacity covers a tiny range of less than a volt, mostly in the 13s. This makes state of charge measurement tricky, especially under load. Sodium is totally different. Its range is vast. For a nominal 12 volts, you start up near 16 volts and end up down in the 6s and 7s. Rumours are that you can even discharge them to 0 without damage. Great for safe transport and storage. This sounds useful, but will be very demanding on voltage regulators in devices these batteries may power. Empty for these batteries is tough to define. You can remove BMS discharge limits, that is BMS, battery management system, and literally drain them all of charge, totally, but most batteries will break if you do that, and most devices will stop asking for power long before you get there. Only very advanced batteries, so-called deep cycle ones, claim to be able to go down to 20 to 30% capacity, and that will still limit its lifetime of cycles. You are unwise to discharge cheaper lead batteries much below 50%, so your usable capacity in real-life sensible use may be much less than the capacity the manufacturers market, and that's before taking into account the current you're drawing, temperatures and so on. Perhaps sodium will buck this trend. This is what I've set out for the approximate start point of each battery, all got through the bulk and absorption phases of smart charging in their appropriate voltages, and then into float. I then disconnected, rested and measured the voltage. Good. Here below in my chart I've laid out, and this is where the episode becomes fraught with battery politics and inevitable controversy and troll feeding, the estimated voltages at various discharge waypoints, down to empty, whatever on earth empty means for a rechargeable battery. Now it's time to discharge. Many moons ago I did a battery test, looking at AA types, and it was basic, almost qualitative. I ran an axial fan through a voltage regulator and measured voltages at increments. Now, we're not exactly cutting edge this time, and I'm aware people have expensive battery analysis machines which feed live data into software, but we're catching up a little. I have what I've named Battery Amperage Regulating Recorder Yeti, or Barry for short. It does not record, nor is it Bigfoot, but I needed to make the acronym work. Barry was cheap, bought on AliExpress, and has the worst user interface on the planet. Barry also can't spell menu any better than it can find a proper word for the letter Y in Barry. But moving swiftly along. We're doing a series of discharges with Barry, and then, in between, the Victron can undo all that wanton waste. The first discharge I felt was rather kind. At a low current, well below even half C for these small batteries, and in a warm room, this should give them a chance to show their very best characteristics. But we're not using a fixed current, as that would be unfair. Barry can do constant power as well. This is far more realistic, as a device being powered needs a certain number of watts, not a fixed current when the voltage is necessarily changing with time. Power regulators take care of this in our electronic devices. It would be unfair to ask for, say, 5 amps from a battery operating at 16 volts, and from another running at 8 volts. The latter is asking for much less juice. So we begin at 15 watts, and the old tech first, sealed lead acid, and fully charged at a fraction over 13 volts. Bog standard, cost me about 12 quid. I started drawing power and let Barry do the work. I'm not running a continual measurement like those software-driven machines can, but instead this is my system. We stop at increments along the way, recording the underload voltage at the start and finish of each segment. We then rest and allow the voltage to recover, record that and move on. I'm going until one of a number of things happen. Either the voltage suddenly tumbles down, which means we've reached the cliff edge of the discharge curve and are out of juice, or a BMS shutoff kicks in, if the battery has one. I'm not too worried about letting them run super low, as these are test units and so I don't care if we damage their cycle life. Here's the gradual discharge of the lead acid, and then the finished state. This first 12 watt hours gives moderate voltage drop during the work phase, and then recovers to about 12.5 volts. On the chart, the marks are made to detail the voltage upon load applied, voltage at the end of the loading, and then the rested voltage before the next phase of discharge, here. 24 watt hours is drawn without drama. On the third go, the voltage under load drops down below 11.5 volts, which at modest current is rather low. I stop and let it rest. We end up measuring just under 12 volts, which is the point at which our internal alarms go off to say stop discharging a lead acid battery. I'll add a red line on the charts to show the subjective level at which we should start worrying about load voltage for each battery chemistry's long-term health. Only 3 amp hours has been drawn, exactly that amount in fact. So this is where the claimed capacity of a battery and realistic cycling diverges. We could go further and even eke out the full 4 amp hours, but we'd knackered the battery in short order. We're getting pretty much the rated capacity, so this is an honestly marketed battery, but of course you wouldn't want to discharge a lead battery this deep if you want it to have much cycle longevity. Next, we'll go across batteries at each discharge speed, as I think this is clearest. The current gold standard for high-performance vehicle and house batteries, lithium iron phosphate. At this gentle discharge of just over an amp, the battery isn't particularly stressed. You get a quick initial drop from fully charged voltage, but there's not much actual charge held within that first volt or so. Then the curve is, if you look at the scale on the y-axis, as flat as we know to expect from lithium iron phosphate. All the activity happens within the range of less than a volt, if you discount those dips and recoveries caused by loading and then resting each phase. We stroll through 24 watt hours, but then a sudden drop. A drop to an underload voltage that trips the low cutoff I set on Barry. It wasn't the battery's BMS, oddly. Why? Well, people of the channel, I was missold the battery. It was tricky to source 3 small batteries for all chemistries with the same rated capacities. I thought I had, but the sales literature was wrong. One document said one thing, and then buried in the small print, a contradiction. It turns out the model with 4 in the code is in fact only a 2 amp hour battery. Cheers for that, hopeless retailer. But to its credit, we do get nearly the 2 whole amp hours of usable range, unlike the lead acid battery where using the fourth of the 4 amp hours would be damaging. So we have a compromised test, although we can still definitely get a sense of the behaviour of this chemistry type. After all, it's the observation and comparison rather than the dataset that will be of use here. I tried to source the right one, but stock issues meant that this would delay the episode for months. I'm an impatient sort. Okay, 2 batteries perform well in this easy challenge, and measured voltages match expectation. Now the newcomer that you're actually here for. We applied the same 15 watts discharge pace and got this. You'll notice it's controlled and steady, but far steeper than the lithium. This matches the wide voltage range we knew to expect. We don't get the full 4 amp hours, about 0.3 amp hours off in fact before we hit the ultra steep final section of the discharge curve. That's no major drama, but could do better. We could blame it on those people in the marketing department over-optimistically rating the cells, and not on the fundamentals of the chemistry. Another thing I noticed is how little recovery is needed after unloading the battery into rest. There's only a little voltage rise at rest each time. And this isn't an observation as you'd know this before running the test, but at constant power the wide voltage range means that you only draw a low current at the start, and then it will draw a current more than double that by the time we're getting towards an empty tank. This will impact cabling, monitors and other parts of your electrical system. Slow discharge done, and now to a medium one, around 1C for the batteries, or rather it should be for the lithium, but due to the mix-up it's in fact double that. For a crank battery for small engines it's not asking too much. First though, I used the Victron to squash all that electricity back into them. No surprises here. At just over an amp, and using custom parameters I set for each, they got back almost the same amount of charge that had just been taken from them. That said, it would have been extraordinary for such an easy discharge to prematurely age a battery so much as to reduce its capacity. 45 watts, and back to our dinosaur entrant, the lead acid. I won't waste your time. A similar result, although a 10% reduction in capacity. Only 2.7 amp hours drawn before we get into the danger zone of the rested battery measuring 12 volts or less. Our titschier than advertised lithium iron phosphate again too. Not much to report. It gives us almost an identical capacity, and I did another little blast to extract a further 0.06 amp hours by using a lower cutoff on Barry. A good battery. Let's draw 45 watts from the sodium ion battery. Performance is staggeringly similar to at 15 watts, almost all the numbers are the same, and a similar total energy drawn, which given acceptable error tolerance for the measuring devices, the charger and so on, this means sodium is resilient, for now. Let's now ask for rather more from our trio of little black boxes. 120 watts, which is bouncing around 10 amps depending on who of the trio you are and when it's being drawn. This is more than 2C for the lead and sodium and more than 4C for the lithium, but it should still be able to handle that. Don't forget the necessary charge first with my little blue machine.
Bernard.
1 amp is slow, but needs must if you want wide voltage control with small batteries like this. Are there any faster, affordable Bluetooth chargers on the market that allow fine control over charge voltages at various phases? You tell me. They all took a full charge once again, plus or minus. The lead battery was having a harder time of it. The voltage dipped a lot more than before whilst loaded up, and was soon struggling to get to the 12 volts at rest I wanted in order to confirm it was healthy. Do note once again that the x-axis is not linear, as I want to show some more detail, and also where the planned waypoints at 12 watt hour intervals are not met, and to show how short they come of the target of 48 watt hours. It's game over at 2.4 amp hours of discharge, the battery's apparent capacity at a high-ish drawn current. The lithium battery, given it's smaller, does well. The first resting voltage after 12 watt hours is similar to at the lower currents, but the voltage drop under load is considerable, into the 11s. The second phase is tough, and it drops down below 9 volts, but after rest gets back closer to 12 volts. This is a deep discharge for nearly any battery, but I pressed further and managed to get more than the rated 2 amp hour capacity, but the cutoff on Barry saves the day at 7 volts under load, after which the recovery to 11.85 volts is rather low, but not terminal. It'll charge fine with 2.3 amp hours in fact, ready for the extra tough 4th round. Before that, we need to see how Mr. Sodium handles the 120 watts. It'll be well under 10 amps at the start and well over at the end, due to the voltage profile. The graph shape and numbers are similar to the 45 watts attempt. We only get to 3.7 amp hours discharge capacity again, and again the BMS doesn't trip. I wonder if they forgot it. Anyhow, once the voltage free fell below 7 volts, I called a halt. Exactly 3.7 amps goes back in once again from the Victron charger. Many of you know that I mess around in the cold a lot professionally, and in my demanding list of battery characteristic must-haves is sub-zero performance. Discharge is one thing, and we know lithium of various sorts is actually pretty good at holding capacity when deep frozen, But we also know it's unwise, or even dangerous, to charge batteries, including lithiums, well below freezing. Sodium promises better. We'll discharge first to compare with each other and to their performance in the warm, and we'll do it at the medium power, 45 watts, in my domestic freezer. The coldest I can get mine to is about -22, -23 degrees Celsius, but the silicone wires can squish neatly in the door seal so that all that precious coldness is trapped within and that Barry can stay outside. All batteries are pre-frozen, so their innards are not left warm. Lead first. Lead acid is not known for cold weather credentials, and you need to compensate with the charge controller, but they shouldn't randomly explode or ignite on you. A hearty full charge later, and the first 12 watt-hours discharge goes well, 12.5 volts after a rest. The second portion really hits hard, and Barry reports 7.5 volts, and so I stop the torture. The lead acid only manages to offer me about 20 watt-hours, which is below 1.8 amp-hours for a 4 amp-hour battery. I applied the same charging routine in the freezer. It recovers to 12.46 volts after the charger is removed, and then after warming up in a sealed bag, 12.54 volts, which is far from an empty battery. However, the cold apparently stopped us from accessing nearly half the capacity. Lithium iron phosphate next, and the same set of rules. A full 14.3 volt charge to start. There was some strange behaviour. Barry recorded a major initial dip to 9.9 volts under load, after which the voltage went upwards, still under load, but 12 watt-hours was drawn, and the rested voltage was only a little below where it was at the warm at this point. How odd. The next block had greater impact, and it doesn't manage 24 watt-hours, but still a respectable 1.89 amp-hours for a 2 amp-hour rated battery in the extreme cold, 5% less than when warm. When recharged cold in the freezer and after a long rest, we get 13.65 volts and 13.35 once warm. It accepts more than 2 amp-hours, which shows lithiums can charge cold, but there's no way of knowing what inner damage we've done. In a separate test, we could repeat this cycle 100 times, but in a location where a fire wouldn't make my neighbours cross. Now, our final cycle for this test episode, patient people of the internet. We know that the voltage as a whole is much more up and then down with the sodium, but the voltage drops more than when warm at this power draw. By the time we're at the third set of 12 watt-hours, the rested voltage is below 9 volts, compared to around 11 volts warm, but it fights on. At around 8 volts under load, the drop becomes a plummet, and it quickly ends up hitting, perhaps, the BMS limiter. I didn't give Barry a cut-off this time. That said, it might have been Barry after all, as it can stop the discharge when it thinks a battery is disconnected, which it might have done. Strangely, the energy we've taken is 3.4 amp-hours, only 0.3 amp-hours below its warm performance, so although the voltage profile differs, you still get a highly respectable result. We charged in the freezer like the others and offered its long rest. It approached 16 volts, despite the charge parameters being a little lower, and once warmed settled to a more moderate 15.5 volts. Success, and the app reported a full 4.6 amp-hours had been delivered in the cold charge. I don't think this indicates greater capacity when cold charging, and experts might explain this through a temperature compensation shift not being taken into account. Do tell me. No other odd signs or behaviours like swelling or smells, and so I have no reason to suspect a very long cold charge is damaging this sodium-ion battery. Since this is all about sodium, I want to share a few final observations with you. I decided to try and discharge it warm again for a final squeeze, but seeing if we can A, actually get the BMS to trip, and B, whether it's truly possible to get it close to a claimed 0 volts, and if I can, whether that kills the battery, or alternatively lets me charge it properly after, and so offering a super safe travel state for the battery. I did most of the discharge at a high current, as this episode is delayed enough without doing a 48-hour trickle discharge, but when we got well below 10 volts, I changed to 10 watts, very gentle. This was fine to a point, and then I got to a cliff edge once more, and remarkably saw the voltmeter report below a volt. I gave it a rest, and it recovered back a few volts. Then back to discharge, but at 3, 2, and then 1 watt. It did the same thing really, gradual voltage reduction, then a dramatic drop-off to half a volt, and then recovery of sorts under rest. So no, I cannot get the battery to trip its BMS, which is a manufacturer slap on the wrist, not a black mark against sodium tech, and I cannot get 100% discharge, but 5 volts or so is very low for a 12 volt battery, and whilst any charge could still shortcut or otherwise get excited, indications are at least that sodium ion isn't likely to thermally run away due to its higher internal resistance. I did a final charge for this hyper-depleted battery and squeezed 3.8 amp hours into it, which is 0.1 amp hours nearer to rated than any previous warm charge. I'm not sure what actual chemical sodium compound is in these batteries, the specifications don't say, and the more general searches show that there's likely to be, in the fullness of time, a family of sodium-ion batteries combined with different molecules into a choice of compounds, rather like the lithium ones that we have access to today. This was also the most expensive of my three, but this may correct once scale gives us economy and adoption is widespread. The barrier to that proliferation will partly be power regulators and chargers. At present, barely any chargers can do the job, and most 12-volt devices would have a fit if asked to use an impulse voltage that starts at 15 volts and still has half of its capacity left below 10 volts. My conclusions: robust, hard to abuse or turn into a fireball, promises of a long cycle life, an easy working life in cold places, and whilst chemically limited in energy density, there are already ideas of how to increase this with graphene and other additives. Sodium won't totally replace what stands today, but it's worth our attention. And of course, this isn't going to be the end of the story, because we're now looking at other sorts of batteries too. We have solid state. Well, knock me down with a little black box and a Victron charger. That might be another thing to test before we decide what's going to go inside Project Bernard. Bye.